In Chapter 6, Section 5, we're going to use the distance formula to help us derive some sum and difference identities. All right, so we are going to be deriving identities using some graphs. Okay, so here we go. Distance formula. As a reminder, the distance formula gives us the distance between any 2 points on an xy coordinate plane, where the distance is equal to the square root of, and this, the distance formula comes from a usage of our Pythagorean theorem, because we can make a right triangle using any 2 points on our coordinate plane. We just look at the distance between the x values squared, and we add to that the distance between the y coordinates squared. Okay. In past sections, common angles have been found and memorized, our unit circle approach. But what if you're asked to find the measure of an angle that's not memorized and to do it without a calculator? For example, what if we want the values that go along with cosine of 15 degrees? Well, one method for doing this would be to rewrite the angle in terms of angles that we do know. For example, cosine of 15 degrees is going to be equal to the cosine of 45 degrees minus 30 degrees, because 45 minus 30 gives us our 15 degrees. But how does this help us? Your first thought might be that we could just kind of distribute the cosine function inside our parentheses here, and see if that works. We need to check and see if cosine of 45 degrees, cosine of 15 degrees is going to be equal to the cosine of 45 degrees minus the cosine of 30 degrees. Is that a true statement? Well, if that's true, then the cosine of 15 degrees should be, the cosine of 15 degrees would be, looking at your unit circle if you can't remember, cosine at 45 degrees is square root 2 over 2, and I would subtract from that the cosine at 30 degrees, which is square root 3 over 2, and this is going to give me a negative value. Square root 2 over 2 minus square root 3 over 2 is going to give us a negative value. Well, if you plug that into your calculator, it's approximately, let's say, 0.1589. Can that be the cosine function value for 15 degrees? Well, think about it. 15 degrees is going to be here in quadrant 1, right? Cosine is going to be positive. So there's no way that this can work. There's no way that's true, because cosine of 15 degrees is going to be a positive value. Is it even close? Let's plug in here and make sure we're in degree mode. What is the cosine of 15 degrees? Well, it's 0.96, so it's not even close. We can't even just like convert that somehow. That didn't work. So we know that this doesn't work. This method doesn't work. We can't do cosine of one angle minus cosine of the other angle, even though we do know that this is a true statement. So how can we use this to help us find the exact value of the cosine of 15 degrees? Well, we're going to use our distance formula to derive a cosine difference identity, where we can subtract two angles and find the cosine of the smaller angle. So let's walk through this proof. To do this problem, an identity is needed for the difference of cosine. That's what I just said. We're going to derive this cosine difference identity, cosine of alpha minus beta. So we're going to find a proof of cosine A minus B and cosine A plus B, cosine difference and cosine sum identities. Consider the following unit circle with angles alpha and beta. You can see alpha rotates to here and beta rotates to here. So the difference between the two is this angle right here. This is alpha minus beta. The length of P1, P2. Where is P1, P2? This is point P1 right here. So this is point P1, this is point P2, so this is that length. the distance of the length of P1, P2 can be found using the distance formula. X coordinate, Y coordinate. So my X coordinate corresponds to cosine, my Y coordinate corresponds to sine. So we can look at the cosine of the first angle, cosine alpha minus cosine beta, quantity squared. And then we add to that sine alpha minus sine beta, quantity squared. So we're using the coordinates for point on angle beta and a point on angle alpha. It doesn't matter which angle you start with here, because when you square that difference, it's going to become positive. Okay, so algebraically, let's work through some of this. When I square a binomial, for this one I would get cosine square alpha minus 2 cosine alpha cosine beta plus cosine square beta. That's this first binomial squared, and I'm going to add to that the second binomial squared, which is going to give me sine squared alpha minus 2 sine alpha sine beta plus sine square beta. Now let's see what we can combine. I've got cosine square alpha and sine square alpha, and using the Pythagorean identity, cosine square alpha plus sine square alpha is 1. I also have cosine square beta and sine square beta, which is 1 again. So 1 and 1 is 2. And then I still have minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. Those other terms don't go away. All right, notice that P1, P2, that distance, is a segment across the angle alpha minus beta, right there. If we rotate this angle so that it is in standard position, so all we did, we took this angle that we measured, we rotated it down so it's in standard position, we get the following. We get a length of A P3, where this is A, this is P3, which is the same distance that we measured here. But using the coordinates for these 2 points now, we would have cosine of alpha minus beta minus 1, quantity squared, plus sine of alpha minus beta minus 0, quantity squared. Okay, now let's square those binomials. So we get cosine square alpha minus beta, and then we get minus 2 cosine alpha minus beta plus 1. And then this with the 0 is a little bit simpler. We have plus sine squared of alpha minus beta. Anything times 0 is 0, so that's the only term left from squaring that binomial. Okay, let's see what we can do there. We have cosine square alpha minus beta and sine square alpha minus beta. That's 1 because of my Pythagorean identity, plus this one is 2. So 2 minus 2 times cosine of alpha minus beta. Okay, now remember I pointed out that this angle and this angle, these are the same, which means this distance and this distance is the same, which tells me that this result is going to be equal to this result. Let's look at that on the next page. Since those 2 distances are the same, we use substitution and we set our 2 results equal to each other. Well, let's square both sides. Algebraically, you can do anything to 2 sides, the same thing to 2 sides of the equation to balance the equation, to keep the equation balanced. So if I square both sides, that is going to undo the square roots. And that leaves me with 2 minus 2 cosine of alpha minus beta equal to 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. All right, I'm going to subtract 2 from both sides. When I subtract 2 from both sides, I have negative 2 cosine of alpha minus beta. Alpha minus beta, yeah, that's right. Minus 2. And you know what? I've got a negative 2 in front of both of these terms, so let's factor that out. Negative 2 times cosine alpha cosine beta plus sine alpha sine beta. And then I can divide both sides by that coefficient negative 2, and that divides out. And it leaves me with cosine of alpha minus beta, cosine difference, is equal to cosine alpha, cosine of the first angle, cosine of the second, plus sine of the first angle, sine of the second, sine alpha, sine beta. Awesome. That is my cosine difference identity. Now, what about the cosine sum? Well, because the cosine function is an even function and the sine function is an odd function, the sum identity can be derived like this. Cosine of alpha plus beta is the same thing as alpha minus a negative beta, right? Because that would go away and become alpha plus beta. So let's reword this to say cosine alpha cosine of negative beta, because this is cosine difference identity. Cosine of the first angle, cosine of the second, plus sine of the first angle, sine of the second. Now, cosine is even and sine is odd. So that means that cosine of alpha plus beta is equal to, this is an even function, so that goes away and is cosine alpha cosine beta. This is an odd function, so I bring that negative out front, minus sine alpha sine beta. And that is my cosine sum identity. All right, so we showed you how to get, we derived both of those identities. And here they are in a nice box so you'll remember them. If I'm doing cosine sum, I subtract. If I'm doing cosine difference, I add. But notice the pattern is the same for both identities. Okay, we are not going to derive every identity that we use, but we derive some of them, several of them, so that you see how we get to them. Because understanding how these values work together is part of doing calculus. Okay, so let's put them to use. Let's go back to our original example. We wanted to know the exact value, not the approximate value, so we can't use our calculator, the exact value of the cosine of 15 degrees. Well, cosine of 15 degrees is going to be the same thing as cosine of 45 degrees minus 30 degrees, so we're doing cosine difference. Let's set that up using our cosine difference identity. 45 is our first angle, alpha. 30 is our second angle, beta. So we have cosine of 45 degrees, cosine of 30 degrees, plus sine of 45 degrees, sine 30 degrees. Now we plug in what we know. We know all four of these values from our unit circle because these are special angles. That's why we chose them. Cosine of 45 is square root 2 over 2. Cosine of 30 is square root 3 over 2, plus sine of 45 and sine of 30. From that, I get square root 6 over 4 and square root 2 over 4, which I can rewrite as square root 6 plus square root 2 over 4. Or what you're going to see, now this is an absolutely acceptable answer, but in my math lab, you're going to see this written as 1/4 times the square root 6 plus square root 2. Those are equivalent ways to write that answer. This is what you're going to find in my math lab for this book. Okay, let's do another example. Sum and difference formulas can be used in reverse, as in I can start with this right side and use it to give me the left. For example, find the exact value of cosine 40 cosine 80 minus sine 40 sine 80 Well, my first angle listed is 40 degrees and my second angle listed is 80 degrees. This is an example of my cosine sum identity. So this is going to be the same thing as the cosine of 40 plus 80 degrees, which is 120 degrees. And that's one of the special angles on my unit circle. The cosine function value at 120 degrees is a negative 1/2. Notice that I don't go to decimals unless I'm told to approximate. Okay, using these sum and difference formulas to establish or verify identities. Find an exact value of cosine pi half minus theta. Well, we are going to notice that we have a cosine difference identity set up where pi half is my alpha and theta is my beta, my second angle. I'm going to be able to plug in values for pi half. Theta is just any angle, so I can't plug in values for it. Let's see what we can do with this. First, let's just apply our identity so that we have cosine pi half cosine theta plus sine pi half sine theta, and then I plug in what I know. Well, the cosine at pi half is 0, and the sine at pi half is 1, and anything times 0 is 0, so I'm left with sine theta. Now, this cosine of pi half minus theta is equal to sine theta is actually my cofunction identity. Our cofunction identities tell us that the cofunction of an angle, that the function of an angle is equal to the cofunction of its complement, where an angle and its complement add to pi half or add to 90 degrees. That's going to be one of our other identities. Okay, so now let's do sine of pi half minus theta. We're going to use these results that we just found to help us out. Sine of theta equals cosine pi half minus theta. That's what we just found here. So sine of pi half minus theta is equal to cosine of pi half minus this angle. So think about this as being, let's see, how do we want to do this? We want to do this as alpha and beta, and that's beta. Oh no, it uses it just as theta. So we think of this whole thing, I don't know why it didn't rename it. That is my kind of my big theta that we are going to say, okay, so replace on the right side, theta was replaced with pi half minus theta. So if I do pi half minus pi half, that cancels out, right? So I have cosine of negative theta, and cosine is even, so that's just cosine theta. That's another example of my cofunction identity. Okay, let's do the proof of sine alpha plus beta. So this is a sine sum, and then we're going to do the sine difference identity. Using what we've found so far, we're going to find sine sum, and then we're going to come down here and do sine difference. So we showed that sine theta in our example 3 at the top of the page, sine theta is equal to cosine of pi half minus theta. So if we do alpha plus beta in place of theta, we have this. So theta was replaced with alpha plus beta. Now as I work through here, if I distribute my negative, I have pi half minus alpha minus beta. So cosine, now this is a cosine difference identity. Cosine of this first angle times cosine of the second, plus sine of the first angle, sine of the second. All right. Cosine of pi half minus alpha is equal to sine of alpha. That's what I started with. And then I've got cosine beta right here. So then this one is going to be cosine alpha, because of my cofunction identity, sine of beta. So there is my sine sum identity, sine of alpha plus beta, sine sum identity derived. Now let's derive our sign difference identity using what we've already figured out. So we just rewrite alpha minus beta as alpha plus a negative beta. And using our sign difference, or finding sign difference, we've got sine sum right here. So sine of our first angle, cosine of our second, cosine of our first angle, sine of our second. And then we use our odd and even identities. So we've got sine alpha, cosine is even, so that's just beta. And then this negative, we have to deal with that, right? So this is minus times minus sine of beta. So that negative is going to end up right there. So that I have sine alpha cosine beta minus cosine alpha sine beta. And that is my sign difference identity derived. All right. Good job. Now, you are not going to be asked to derive these identities on your own. You're going to be tasked with using them. Okay, so those two identities that we just derived, sum and difference for sine, right there you go. Now we're going to use them to find some exact values for not special angles. If we know that the sine of alpha is 3/5, and we know that alpha is in quadrant, pi half to pi is quadrant 2, and we know that our second angle, sine of beta, is this, so negative square root 5 over 5, and we know that beta is going to be in quadrant 4. So alpha is in quadrant 2, beta is in quadrant 4. Find the exact values of cosine alpha, cosine beta, the cosine sum, and the sine sum. So we've got to find some missing values first for each of the individual angles, and then we'll use our cosine and sine sum identities. Okay, our first angle, alpha. Let's sketch it into the correct quadrant. It's in quadrant 2. Sine is 3/5, so y is 3, r is 5, and we need x, right? This is, I'm so sorry, this is our alpha. We need r. So, no, we need x. We know y and we know r from our sine function value. So we need x, and we know that x is going to be negative because we're in quadrant 2. That's why that absolutely matters. So x squared plus y squared equals r squared gives me x equals square root of, well, r squared is 5 squared minus 3 squared. 5 squared minus 3 squared, 25, minus 9 is 16. So x is going to be a negative 4 because we're in quadrant 2. If you hadn't sketched it, you might have forgotten that needed to be a negative 4. So cosine of alpha is a negative 4/5. That's what we were after there. Now let's find cosine of beta. We know sine beta, so let's sketch it into the correct quadrant. Beta is in quadrant 4, so we're down here. We start with sine function value. We know that y is a negative 1 and r is a square root 5. We need to come up with x, and in this case x is going to be positive. So x is equal to the square root of r squared minus y squared. So 5 minus 1 is 4, and x is going to be a positive 2 here because we're in quadrant 4. The cosine value of beta is 2 over square root 5. Alrighty, let's work this out now. We're going to do cosine sum and sine sum identities. Cosine sum identity, our pattern is cosine alpha, cosine beta minus sine alpha, sine beta. We were given the sine function values, we found the cosine function values. Cosine alpha is negative 4/5. Cosine beta is 2 over the square root 5 minus sine alpha was 3/5. Sine beta was a -1 over square root 5. My denominator here, my common denominator, is 5 square root 5. My numerator, -4 times 2 is -8, minus a -3 is +3. So that gives me a -5 over 5 square root 5 that I need to rationalize. So I'm going to rationalize by multiplying by square root 5 over itself, which gives me a negative, those 5s are going to cancel, aren't they? So I get a negative square root 5 over 5. Okay, now let's do sine sum. My sine sum identity is sine alpha cosine beta plus cosine alpha sine beta. Using the values we found and the values we were given, we have 3/5 times 2 over square root 5 plus a -4/5 times a -1 over square root 5. Again, we have that common denominator of 5 square root 5. And in our numerator, we have 6 plus 4. So let's rationalize. That gives me 10 square root 5 over 25, which simplifies to be 2 square root 5 over 5, leaving it exact. All right, excellent. Now I'm just assuming that you guys are slowing me down by pausing the video as needed. Let's go ahead and move on to exploration number 5, where we find the proof of the tangent sum identity. We're going to use the quotient identity for tangent, so that tangent theta equals sine theta over cosine theta, to derive or develop our tangent sum identity. Okay, so given our quotient identity for tangent, we can rewrite tangent sum as sine of alpha plus beta over cosine of alpha plus beta, and we know both of those identities, so let's fill those in. Okay, so double check your identities, make sure you have your algebraic signs plus and minus correct. Now, I'm going to divide by a well-chosen one. So I'm taking my numerator and denominator and I'm dividing by a well-chosen one, cosine alpha, cosine beta. So I put my numerator over cosine alpha, cosine beta. So sine alpha cosine beta plus cosine alpha sine beta divided by that well-chosen one, and then my denominator also divided by the well-chosen one. So I'm just recopying those identities that I filled in the previous step. And then I see what I can simplify. Now, the way they write this is a little squirrely. I kind of protest, but we're gonna do it. It's gonna be okay. So make sure that you have divided. So we're just looking at the top and then the bottom of your identity or your problem here. So right here, I have cosine alpha, cosine beta as my denominator for this top piece. Notice that if I were to split this so that I wrote my numerator as two separate terms, sine alpha cosine beta over cosine alpha cosine beta, the cosine betas are going to cancel. Let's go ahead and write it down though. Sine alpha cosine beta. So we split our numerator into two separate pieces. Now I'm going to look at those two separate pieces just of the numerator, and I see that my cosine betas cancel. So this first term in the numerator is sine alpha over cosine alpha. And the second term in my numerator is sine beta over cosine beta. And then I look at my denominator. and I rewrite my denominator as two separate terms with the same denominator, the same bottom piece. So I have cosine alpha, cosine beta, and sine alpha, sine beta, and I look to see what cancels here. I cancel those cosine betas, so I'm left with cosine alpha, did I miscopy? Oh, no, I didn't miscopy. That cancels to 1, doesn't it? I wasn't paying close enough attention. That cancels just to be 1. And then this one cancels, nothing cancels. So that gives me sine alpha. Let's change that to sine alpha, cosine alpha, and sine beta, cosine beta. Ah, goodness gracious, I apologize. This first term, these numerator and denominator are equal, so that's just 1. And then I have sine alpha, sine beta, cosine beta. I'm split that again. All right. Now, let's go to terms of tangent. Sine alpha over cosine alpha is tangent alpha. Sine beta over cosine beta is tangent beta. And right here, I've got tangent alpha times tangent beta. Tangent alpha times tangent beta. And that, my friends, is tangent sum identity derived. So again, don't panic. I'm not going to make you do these on your own. This is a good way for us to see how we get these identities, how they fit together, and how we practice manipulating these terms, these trigonometric functions. So that was tangent sum. Now we're going to do the proof for the derivation of tangent difference. Because tangent function is odd, we can find the difference identity by using a negative beta. So alpha minus beta is the same thing as alpha plus a negative beta, which would give me tangent alpha plus tangent of a negative beta. This is the tangent sum identity that we just found. We're using tangent sum. 1 minus tangent alpha tangent of negative beta. But again, tangent is an odd identity. So my numerator becomes tangent alpha minus tangent beta, and my denominator becomes 1 plus tangent alpha tangent beta. And here we go. Both the sum and difference identities that we just derived, all in a nice little box for you. Okay, example 5 is the last one we're actually going to do. We're going to skip example 6. So let's work through example 5. We're going to use the sum and difference formulas with inverse trig functions. So we're going to find the exact value of the sine of this angle, and this angle is a difference. Okay, so first thing, let alpha be sine inverse of 3/5. So this is alpha. Alpha has a y coordinate of 3 and an r of 5, and we will need x, right? Or we can use I'm looking at my notes because I think that we do this a little bit differently. Sine alpha, cosine beta, and then I'm using the Pythagorean identity. Okay, instead of sketching angles. You can sketch angles here, and that's what I was expecting to do, but my notes recommend, and I assume that's because my math lab does it this way. Cosine square alpha plus sine square alpha is 1, our Pythagorean identity, correct? So that means that if I solve for cosine alpha would be the square root of 1 minus sine squared alpha. If I rearrange the Pythagorean identity and solve for cosine, that gives me cosine alpha is the square root of 1 minus, And then sine alpha is 3/5, so that would be 3/5 squared. Well, 3/5 squared is 9/25, and 1 minus 9/25 is 16/25. So cosine alpha is the square root of 16/25, which is 4/5. So cosine alpha is 4/5. Now we know for beta, we have information about cosine instead of sine. So we're going to need to solve for sine. So instead of cosine alpha here, I'm going to use sine alpha is equal to 1 minus cosine, or sine beta, excuse me, sine beta is going to be equal to 1 minus cosine beta squared. Well, negative 4/5 squared is 16/25. And 1 minus, so sine beta equals 1 minus, so 25 minus 16/25 is 9/25, which is 3/5. So there's my sine beta. Now I'm going to rewrite as the formula for the sine of the difference of two angles, because that's what I have here. I have angle alpha and I have angle beta, and I've got sine of sine inverse minus cosine inverse. So what I'm wanting is the sine of the difference of alpha and beta. So I want sine difference of alpha and beta, where this is my information about alpha and this is my information about beta. My sine difference identity is sine alpha cosine beta minus cosine alpha sine beta. And then I plug in what I have found and what I know. I know the sine of alpha is 3/5 and the cosine of beta is a negative 4/5. I know the cosine of alpha is 4/5, and I know the sine of beta is 3/5. So when I do this multiplication, this first term is a negative 12/25 minus positive 12/25, and a negative 12 and a negative 12 is a negative 24/25. That is the sine of the difference of these two angles. All right, guys, and like I said, we are going to skip example 6. All right, there we go.